This is America in Space, a weekly news and information program on current events dealing with the space industry.
Welcome, and thanks for joining me today. I'm Dawn Meyer, Space Coast News Editor. You probably don't usually think of objects in space as musical, and yet NASA has released several musical pieces called sonifications of data from various space probes and telescopes over the years. Since different telescopes can detect different types of light, each brings its own pieces of information to whatever is being observed, similar to how different notes of the musical scale can be played together to create harmonies that are impossible with single notes alone. In the 1990s, NASA recorded the sounds of the planets from data sent by the Voyager 1 and 2 space probes that launched in 1977 and concluded their planetary flybys of our solar system in 1992. That compilation was titled The Symphony of the Planets. In recent years, NASA has been producing sonifications of astronomical data of objects in space. This takes the digital data captured by space telescopes and translates it into musical notes and sounds so it can be heard rather than seen. Each layer of sound in these sonifications represents particular wavelengths of light detected by NASA's Chandra X-ray Observatory, the James Webb Space Telescope, the Hubble Space Telescope, and the Spitzer Space Telescope in various combinations. Here's a piece of the original Voice of Earth recorded from Voyager. Now let's move to the newer process. This first one is of our Aquarii. Our Aquarii contains two stars, a white dwarf and a red giant, in orbit around each other. In a composite visual image, the Hubble Space Telescope data reveals spectacular structures that are evident of outbursts generated by pairs of stars buried at the center of the image. The X-rays from Chandra show jets from the white star banging into the material surrounding it and creating shock waves. In the sonification of the data, the piece evolves like a radar-like scan of the image, clockwise starting at the 12 o'clock position. The volume changes in proportion to the brightness of sources in the Hubble's visible light and Chandra's X-ray image, while the distance from the center dictates the musical pitch. The higher notes are the farthest out. The deep thuds toward the four corners are distraction spikes, which are artifacts from the bright central star. Listeners can hear jets from the white dwarf as the cursor travels near the 12 o'clock and 8 o'clock positions. The ribbon-like arcs captured by the Hubble create a rising and falling melody that sounds similar to that of singing bowls, while the Chandra data is rendered to sound more like synthetic and windy purrs. This next one is Stephan's Quintet. The visual image of Stephan's Quintet show it as four galaxies that each move around each other, held by gravity. A fifth galaxy sits in the frame but is actually a much different distance. The visual image of Stephan's Quintet contains infrared light from the James Webb Space Telescope with additional data from the Spitzer Space Telescope and X-ray light from Chandra. A sonification of this data begins at the top and scans the image downward. As the cursor moves, the pitch changes in relationship to the brightness in different ways. The background galaxies and foreground stars in the visual images that Webb detects are mapped to different notes on a synthetic glass marimba. Meanwhile, stars with the distraction spikes are played as crash cymbals. The galaxies of Stephan's Quintet themselves are heard as smoothly changing frequencies as the scan passes over them. The X-rays from Chandra, which reveal a shock wave that has a superheated gas to tens of millions of degrees, are represented by a synthetic string sound. Personally, I think it sounds a lot like birds. The next one is Messier 104 or M104, which is located about 28 million light years from Earth. M104 is one of the largest galaxies in the nearby Virgo cluster. As seen from Earth, the galaxy is angled nearly edge-on, allowing a view of its bright core and spiral arms wrapped around it. Spitzer's infrared view of M104 shows a ring of dust circling the galaxy that pierces through the obscuring dusk in the Hubble's optical light image. Spitzer also sees an otherwise hidden disk of stars within the dust ring. The Chandra X-ray image shows hot gas at the galaxy and point sources that are a mixture of objects within 104 as well as quasars in the background. The Chandra observations show that diffuse X-rays emissions extend over 60,000 light-years from the center of M104. In sonifying this data, it begins at the top and scans toward the bottom of the image. The brightness controls the volume and the pitch, meaning that the brightest sources in the image are the loudest and the highest frequencies. The data from 3 telescopes are mapped to different types of sound. X-rays from Chandra are like a synthesizer. Spitzer's infrared data are strings, and optical data from Hubble has bell-like tones. The core of the galaxy, its dust lanes and spiral arms, and point-like X-ray sources are all audible features in the sonification of this data. The final one is the black hole at the center of the Perseus galaxy cluster. In 2003, astronomers discovered pressure waves that were sent out by the black hole that caused ripples in the cluster's hot gas that could be translated into a note that humans cannot hear because it's 57 octaves below middle C. The sonification of this data uses the actual sound waves discovered in the data from Chandra. The popular misconception is there is no sound in space. That originates from the fact that most of space is essentially a vacuum that provides no medium for sound waves to propagate. However, a cluster galaxy has copious amounts of gas that envelop the hundreds or even thousands of galaxies within it, providing a medium for the sound waves to travel. In the sonification of Perseus's data, the sound waves that astronomers previously identified were extracted and made audible using sound wave extracted in radial directions, that is, outwards from the center. The signals were then resynthesized into the range of human hearing by scaling them up 57 and 58 octaves above their true pitch. Another way to put this is that they're being heard 144 quadrillion and 288 quadrillion times higher than the original frequencies. And for reference point, a quadrillion is a 1 with 15 zeros. The radar-like scan around the image allows you to hear waves emitted in different directions. These sonifications were led by the Chandra X-ray Center and included as part of NASA's Universal Learning Project. All of this music can be found on various musical sources, and the information about the project is on nasa.gov. Personally, I have the original CDs of the Voyager tour myself. Thank you for joining me. Remember each Tuesday to join David Denault for America's Return to Space, and join me every Friday for America in Space. From the Florida Space Coast, I'm Dawn Meyer, Space Coast News Editor for About Space Today.
Thanks for listening. Be sure to share our program with your family and friends and follow us on Facebook. Join us each week for news and information on America in Space.